All right, this is MCT4C, day 19, first day of the new unit. The new unit is on vectors, and vectors are kind of a new math thing for us. They're not, it's a new way of operating with math stuff, so it's going to be kind of different. If you've taken some physics before, you've probably done some vector um, math in physics. The 3-minute review today is basically just getting right into the lesson, but it's a little bit of a sidebar. And this idea of vectors, one thing that's important is direction. And it's nice to be clear about what direction we're talking about and how we're going to say that. So for instance, here's a boat, and north is this way, and they're heading off in this direction. So how do we describe the boat's direction? Well, there's two kind of common ways. The quadrant bearing is an angle between 0 and 90 degrees measured east-west of the north-south line, which sounds crazy, but you just go north or south first, and then the angle west or east. So in this case, the boat is going, well, north first, but then 40 degrees west. North, 40 degrees west. Verbally, you hear some teachers would say that 40 degrees west of north is verbal. I'll never write that because it's too many letters. That's what I'll write right there. A second way of talking about direction is the true bearing. True bearing is essentially you put a line at true north, right like this, and it's the number of degrees from true north. That's it. And it's a 3-digit number from true north. So here, if I wanted to talk about this one, well, if true north is 0, how many degrees are you from true north if I rotate this way, similar to this compass here? Well, 360 is all the way around. 360 minus 40, there's the true bearing, 320. All right, we got some examples. And notice that, just to keep you on your toes, the quadrant bearing is over here, and the true bearing's over there, and we want to describe this canoe, their direction. Well, if that's 60 degrees, this would be the true bearing here. All the way from north to south would be 180 degrees minus 60 is 120. There's the 3-digit number. It's just that easy. For the quadrant bearing, this boat is headed south, but then east of that direction, right? West is over here. East is sort of off to the right. So we can say south first, but then 60 degrees east. Now, if I don't ask which direction, you can pick whichever one you like the best. Usually what I'll do is whatever is described in the question, I'll give the answer in that bearing. Okay, so this time we're given a quadrant bearing, and we have to sort of figure out the true bearing. South, 10 degrees west. I like having a picture here. I'm not going to draw any boats, though. North and south. So south, but then 10 degrees west. West is left. South, 10 degrees west. So this is 10 degrees west there. The true bearing is from north all the way around. There's 180 plus 10, 190 degrees is the true bearing. Over here, a true bearing of 90. So if that's 0, 90 degrees from there is this direction here, isn't it? Well, what direction is that? Now, we would never write this, but we could say it's north 90 degrees east or south 90 degrees east, but no. This is just plain east, isn't it? East. Done. Okay, on to the lesson. A vector. Recognize and represent vectors, including those that arise from real-world applications. So this idea is a vector is a new math thing, and we use them in certain situations. A vector has two things that's true about it. Every vector has a magnitude and a direction. We just talked about directions. So magnitude means a size. Numbers have size. 5 is bigger than 4. Just like vectors, some are longer or shorter. We'll see geometrically a vector is represented by a directed line segment. So I'm going to get my directed line segments out. This is what it looks like, something like this. So I can see the magnitude here is just how long, like how long is this line segment. That's the magnitude, and the direction is kind of the angle that this is shooting off in. And so we represent certain quantities in math, in real life, using these items. Draw a scale diagram to represent each vector quantity. Now this is kind of tough for me, because where's the ruler come from? Now I think there is a ruler built in, so I'm going to do my best here. But there's a ruler, and it might take me a second to situate this correctly. And your scale and my scale aren't going to match up that well, perhaps, but I want to draw a line that represents 60 kilometers per hour due west. And how am I going to do that? Well, I know just a little west is this way, right? So I want to draw a line segment 60 kilometers an hour west. Well, I'm not going to draw it 60 centimeters long. I'm going to let each centimeter be, let's say, maybe 20 kilometers per hour. And then I know I have to draw a line segment here that is 3 centimeters long to make 60, and then pointed straight west, like that. And then I'd label it with its actual value that it's supposed to be. There's the scale. There's the diagram. And if you want to, you could actually put a little the crosshairs there, so we know that that's north is straight up. Not always will we be talking north, south, east, and west. Like in this second example, we've got this is a force, another physics thing. 15 newtons down. So instead of south, this is down, but that's no problem. Down is down the page. And I'm going to pick a decent scale. So to get to 15 newtons, I might pick 1 centimeter is equal to maybe 3 newtons, say. I gotta turn my ruler now. I might not, will I be able to do this? Let's just see. That doesn't do it. How do I turn the ruler? No, that makes it longer and shorter. That makes it bigger and smaller. Let's see. Can I turn it? Let's see if I can turn this thing. Can I rotate it here? There, unlock. Huh. Maybe I can't rotate it. Well, you'll trust me that down, if I could figure out how to turn my ruler, I'd put this 5 centimeters down. I'd measure it 5 centimeters and push it down. This is why you practice these things on the smartboard before it's game time. 15 newtons. And measure that. So you can measure that. That's exactly 5 centimeters long. All right, scale diagrams, part of vectors. More notes. And we see a whole bunch of vectors, and you see we label vectors with a little line above them to show that it's a vector. A quantity without a direction is called a scalar. These are the quantities that we're used to, by the way. Like, it's in 5 minutes, it's the end of class. Well, 5 minutes doesn't have a direction, right? And in some cases, because there are vector quantities so close, we goof this up. So, for instance, a vector quantity is velocity, but a scalar is speed. Speed, which is, for instance, 50 kilometers per hour. Well, what's it missing? It's missing a direction, right? It's not 50 kilometers per hour west or whatever. Another one that's pretty neat is mass. Mass, which is in kilograms, doesn't have a direction, where weight is pulled upon by gravity. So weight of 3 kilograms down or towards the middle of the earth or whatever is a vector quantity. Mass is a scalar, weight is a vector. Okay, two vectors are equal if they have the same magnitude and direction. That makes sense. So if they have the same magnitude, same length, and direction. That is, position is not important. For example, if I had this vector y, I could draw another vector down here somewhere that had the same directions, point in the same direction. I'm going to call this little vector x here. And they're not in the same position. You know, one is above the other one, but they're pointing in the same direction and they have the same length. That means I can say x is equal to vector y. Okay? We show the magnitude of a vector using these signs, these absolute value signs. Okay? So, for example, we'd say the absolute value or the magnitude of y is 4 units. Right? The vector y is 4 units right, whatever the units would have to be. Notice that, and you can almost picture what's going to happen here. If I was talking about the magnitude of AB, I can't just count how long it is, but yeah, you can see it, can't you? I could use trigonometry to figure out how long that is. So we don't know what that is. One thing that I see, though, is you see how Z and AB have the same magnitude? Because this one is sort of 4 and 3, and this one is 4 and 3. So I could say AB, the magnitude of AB is equal to the magnitude of Z, but, are these two vectors equal? No. Because they're not in the same direction, they're not equal vectors. That's an important distinction, okay? These two vectors are not equal even though they have the same magnitude. More notes, more things about vectors. Vectors with the same magnitude pointing in exactly opposite directions are called, wait for it, crazy name for it, opposites. So we said that x and y are equal, but where's a pair of opposite vectors? Well, we see AB and M are the same length, but they're parallel, pointed in the opposite direction. So I can say that AB is equal to negative M, and that means that these two vectors, AB and M, are opposites when I put a minus in there, okay? Also notice that vector AB, showed by this vector here, is equal to the opposite vector of BA. Now, even though the line's not there, I could say, well, BA is this vector. This point is A, and so B starts there, A. Well, those are opposite vectors, aren't they? Yeah, they're equal in magnitude, but in opposite directions, opposite vectors. Okay, how are we doing for time? 13 minutes. Can I get through this in a couple of minutes? I think I can. I'm just going to pound through. This one will be a little bit long, but it'll only be one today. We've got a parallelogram. Parallelogram means opposite sides are equal and parallel, right? So there's some vector stuff going on here. We're just supposed to say whether it's true or false. WZ is equal to XY. So WZ pointed this way is equal to XY. That's true. Those two vectors are parallel, so they have the same direction, and they're equal because it's a parallelogram. Those two vectors are equal. Dandy. What about XZ and, WX, this vector pointing towards X, and YZ. Are those equal? No, that's not true because they're opposites, right? This one is pointing to the right. Y starts here, YZ is pointing to the left. These are actually opposites. I could say this is true. Or I could say WX is equal to zy, because both of those vectors start at z and end at y are pointing to the right. Is this true? The magnitude of WA is equal to the magnitude of YA. Well, the magnitude, yeah, this one's pointed this way, this one's pointed this way, but those line segments are actually equal. This is true. But are the vectors equal? No, because one's pointed this way and the other one's pointed this way. They're opposites. And I could write them as opposites if I wanted to. False. I think this is the same one, right? WX is equal to XW. No, that's our definition. That's false. These are opposites. WX is equal to negative XW. All right, last example. From home, Ferd walks 5 kilometers west, then 7 kilometers north. Notice no bearings needed there. That's just west and north. And we want to calculate the magnitude of the displacement vector. Displacement is a vector way to say distance. So, I can see the distance that he has walked is 12. Right? I just go 5 plus 7. He's walked 12 kilometers distance. That's distance. Displacement is kind of how far away is he? Well, if I think of vectors, and I'm not going to draw a scale diagram, but if that's 5, he walked 5, and then he walked 7, because he's here now. He walked 5 west, and then he walked 7 north. There's 7. Dandy. Well, how far is he from home? Well, actually, he's walked this distance, hasn't he? And I'm going to... He starts here, and he ends there. Right? I'm going to change the color of that baby. This is his actual resultant walk, right? So if I call that his displacement vector D, here we're just asked to find the magnitude of the displacement vector. Don't mind the phone if you can hear the phone. The magnitude of the displacement vector, well, since west and north are at right angles, this is just Pythagorean theorem. 7 squared plus 5 squared calculate, that's 74. Take the square root of both sides. The magnitude is about 8.6 kilometers. So he's actually 8.6 kilometers from home. And notice, I'm talking about the magnitude, the length of that red vector. The direction, pointing off in this direction, he's some west and some north. Well, I need to find an angle here and then talk about a bearing. And this is what we talked about in the 3-minute review. So if I set this up, the two sides that are given that don't have decimal places in them are the opposite side and the adjacent. 7/5. Little trig action here, doesn't hurt. Theta is about 54 degrees. So, I mean, there's a number of ways to describe that direction, but the way I would think of it perhaps is if this is north, north is here. If this is 54 degrees, how much is this? This is to add up to 90, right? 90, so that would be 36 degrees. And so Ferd is 8.6 kilometers and north 36 degrees west, northwest of home. Or if I wanted to replace that with a true bearing, if that's 36 degrees, this would be his true bearing, right? Which is 360 subtract 36, which looks like it's about 324 about, I think. So you could say that he's on a true bearing of 324 degrees from home. That's it. Good luck with your first day of vectors homework.